Hello everyone, and welcome. Today, we're going to dive into a fascinating presentation titled On Data Engineering for Scaling LLM Terminal Capabilities. We'll be exploring exactly how targeted synthetic data generation can transform a standard 32 billion parameter base model into the benchmark-crushing Nemotron-Terminal. Let's start with the core problem. As terminal interaction emerges as a critical capability for practical software engineering, training these agentic AIs is blocked by a dual bottleneck. First is resource scarcity. We simply lack diverse task prompts and pre-configured execution environments. Second is trajectory logistics. Human data collection is just too slow, and synthetic generation is incredibly expensive because instantiating a fresh environment for every multi-turn task takes too much time and compute. To overcome these hurdles, we built an engine called Terminal Task Gen. This system tackles the problem from two angles, breadth and depth. For breadth, it adapts existing math, code, and software engineering benchmarks into scalable terminal prompts. For depth, it constructs targeted, fine-grained scenarios using a rich skill taxonomy. Both of these streams feed into containerized Docker environments, where an agent, powered by DeepSeek v3.2, executes the tasks and generates multi-turn solution traces. Looking closely at Phase 1, dataset adaptation, we successfully adapted over 226,000 prompts. This includes 163,000 math prompts, 35,000 code prompts, and 32,000 software engineering prompts. The secret mechanism here is pure, scalable formatting. We append domain-specific terminal instructions to the original prompts, meaning no LLM in the loop is required to rewrite the data at this stage. Moving to Phase 2, we focus on targeted depth. We do this in two ways: seed-based generation, which augments abstract mathematical and coding problems with concrete constraints like installing packages or reading I/O paths. Then, we use skill-based generation to synthesize novel tasks across 9 core domains, such as data querying, debugging, and security, forcing the model to combine multiple primitive skills simultaneously. So, how did we scale this without slowing down? The major unlock was using pre-built environments. Historically, generating a unique Docker file for every single task led to massive validation overhead. Terminal Task Gen, instead, uses exactly 9 pre-built, domain-specific Docker images. This results in zero validation overhead for broken environments, a massively reduced container footprint, and decoupled scaling that allows for massive throughput. Once the environments are set, we move to trajectory collection. DeepSeek v3.2 acts as the teacher agent inside an interactive TMUX session. At every single step, the model uses a structured chain-of-thought approach in a strict JSON format. It outputs its analysis of the current state, formulates a logical plan, and then issues precise keystroke commands along with execution durations. During training, we uncovered a fascinating filtering paradox. You might assume that keeping only successful trajectories is the best approach. However, strict data filtering actively hurts performance. A success-only filter yielded about 5% performance, while using absolutely no filter more than doubled it to 12.4%. The takeaway? Retaining failed trajectories exposes the model to realistic error states, teaching it essential recovery and debugging patterns. We also busted some common training myths. Myth 1: two-stage curriculum learning is better. Our finding was that a single-stage mixed strategy actually outperforms it. Myth 2: pushing context length limits improves reasoning. We found that evaluating under the standard 32K context window yields the strongest results. Pushing it to 65K tokens actually drops performance because extremely long-tail trajectories tend to introduce noise rather than signal. All of this engineering leads us to the payoff, Nemotron-Terminal. By applying our new terminal corpus dataset of nearly 500,000 tasks to standard Qwen 3 base models, we unlocked frontier-level capabilities. We created 8B, 14B, and 32B variants. And the training was remarkably efficient. The 32B model required just 16 nodes for 2 epochs, demonstrating the sheer leverage of high-quality data over brute force compute. The benchmark results on Terminal Bench 2.0 speak for themselves. The 8B model saw a 5x increase over its base. But the real story is David versus Goliath. Our 14B model outperformed the 120B parameter GPTOSS model. And our 32B model, at 27.4%, definitively beat the massive 480B parameter Qwen 3 coder. The bottom line is that parameter count alone is insufficient. High-quality trajectory data effectively bridges the gap to massive frontier systems. If we look at a capability deep dive, we see the model didn't just get marginally better, it went from zero to mastery. In areas like data querying and model training, the base model scored a literal 0. Nemotron-Terminal jumped to scores of 60 and 50. It acquired entirely new, functional software engineering and system administration skills that were effectively absent in its original base weights. We also observed a predictable law of scaling. As shown in the charts for the 8B and 14B models, performance strictly and predictably scales with synthetic data volume from 0% to 100%. Capacity matters, too. The larger 14B model exhibits a steeper upward trajectory. The conclusion is that both model capacity and synthetic data scale are critical, compounding vectors for future performance. To wrap up, the secret to building state-of-the-art terminal agents isn't simply throwing more parameters at the problem or building complex scaffolds. It is precise, scalable data engineering. By combining broad adaptation with deep synthetic generation, small models can exhibit frontier-level command line proficiency. And in the spirit of democratizing AI, the model checkpoints and the terminal corpus dataset are fully available to the community on Hugging Face. Thank you.